Hi, we're starting on slide 49 of chapter 6, osseous tissue and bone structure. So we're just finishing up the last part of this chapter before you start your lecture on articulations. So talking about calcium homeostasis, balancing the amount of calcium you have in your bones versus how much calcium you have in your blood, and you have to maintain a very even level of calcium in your blood. And so this is where the homeostasis is very important. So we consider bones as kind of a place that stores calcium and other minerals like phosphate, for example, because we have calcium phosphate. However, we always think about calcium when we talk about bones because calcium is the most abundant mineral we do find. Calcium ions, so that would be like this. They are really important to many functions in the body, important in membranes and neuron function, especially sending signals, essentially. We'll talk much more about that later. Muscle cell physiology and their ability to contract, especially heart cells, so cardiac muscle cells. Okay, so calcium is regulated by two very important hormones, calcitonin and parathyroid hormone. Very frequently, parathyroid hormone is abbreviated PTH, makes life a lot easier. So as I mentioned before, calcium levels need to be very carefully monitored. They have to be at a very narrow range. And so our body has to have a way to maintain blood calcium homeostasis for all of those vital functions we mentioned on the previous slide. So our body is able to help maintain blood calcium ion levels, homeostasis, using these two important hormones, calcitonin and parathyroid hormone. And so these control the storage, so that's at the bone level, absorption, which is at the intestines. That's not writing, sorry. Intestines. And excretion. Excretion is at the kidney. Okay, let me see if I can try to write intestine there. So these are the three main areas that are affected by these two hormones. Okay, so calcitonin and parathyroid hormone, as I just mentioned in the previous slide, control and affect the blood, the calcium deposition or breakdown of bone. So calcium coming or being deposited or being removed from bones. Also affects the digestive tract, whether you're increasing the absorption of calcium or decreasing the absorption if you have too much calcium already. And then finally, the kidneys. In the kidneys, if you have too much calcium in your blood, it will excrete that extra calcium out as urine. Or if you don't have enough calcium, the kidneys will reabsorb any calcium and bring it back into the blood so it's not excreted and lost. Okay, so a little bit more about these two hormones. Parathyroid hormone is made by 4 little tiny parathyroid glands we find hiding behind the thyroid gland in the neck. And this hormone, parathyroid hormone, works to increase calcium levels. Okay? If that's all you remember about this hormone, that's what you want to remember. It works to increase calcium levels. And so this 3 ways that it does that is it stimulates osteoclast activity, which are going to break down bone. It increases intestinal absorption, so you're absorbing more calcium through your digestive tract. And it tells the kidneys to not excrete calcium into your urine. So you're preserving the calcium you have, and you're getting any extra calcium you need directly from your bones. Okay. Then calcitonin is the other hormone, and this is made in the thyroid gland. And so the thyroid gland and the parathyroid gland are basically in direct contact with each other, and they create or secrete hormones that are antagonists of each other. They work opposite of each other. So parathyroid hormone is released to help increase calcium levels in the blood. Calcitonin is released to decrease blood calcium levels. And so the three main ways that you can decrease blood calcium levels. I'm sorry, my little thingy is acting up. Blood calcium levels. You inhibit osteoclast activity. That means your osteoblasts are still active, and so they're still depositing calcium on the bones, but you don't have osteoclasts breaking it down. So you have an overall deposition of calcium on the bone. You also increase calcium excretion, so you're getting rid of extra calcium in your urine. And then finally, you're also trying to decrease your calcium levels. It kind of indirectly affects your intestines, and the absorption for calcium decreases in the intestines. Okay, so I'm going to skip these questions. You can look at these and use them as you study, but I'll just read it quickly and I'll just tell you the answer. So our bodies need calcium for, you can ignore this, but our body needs calcium for all of those functions. What does calcitonin do? If you remember, calcitonin works to decrease blood calcium levels. Okay, so decrease calcium levels in the blood. So that means we have enough already. We have extra. So if we have extra calcium levels, we are trying to find a way to decrease the blood calcium levels. So it is released when blood calcium levels are high. Okay? And when calcium levels are high, we get rid of extra calcium in the kidneys, and we deposit extra calcium on the bone, which number 1 is also true. 2, no, and 3, no. In fact, number 2 and 3 actually apply to your parathyroid hormone. Okay? I'm not going to go over this slide. This is something I want you to do independently. It's also as a handout on Moodle, and it takes you through what's going on with parathyroid hormone. So we see that right there. And also what's happening with calcitonin. So if you look at this right here, this is talking about calcium ion homeostasis in the blood. And if levels go too high, so if you have an increase in blood calcium levels or a decrease in blood calcium levels, this handout kind of walks you through the steps that occur to help bring blood calcium levels back to homeostasis. So I highly recommend you spend some time reading this and studying this, understanding the steps with each scenario, whether calcium levels are too high in the blood or too low in the blood. Okay, this is another great illustration, and it shows you physically in those 3 important areas of the body how calcitonin affects those 3 areas, the kidneys, the bone, and the intestines, and how parathyroid hormone affects those same things. So up here we're talking about parathyroid hormone. Parathyroid hormone acts to increase, you're trying to increase calcium levels because your levels are too low. So you increase by increasing absorption of calcium in your intestines. The osteoclasts are stimulated, so they're working harder to break down bone. And the kidneys, instead of excreting calcium out in urine, retain it in the bloodstream. And so by the action of these 3 things helps to keep your blood calcium levels within a very narrow range, so within homeostasis. Now, the second figure below is when your blood calcium levels are too high. I'm sorry. When you need to decrease your blood calcium levels. So calcitonin, as we remember, works to decrease calcium levels. And so It affects the intestines by decreasing how much calcium is absorbed. It stops osteoclast activity, so the osteoblasts have a chance to actually deposit bone. So I'm just going to put blasts. So osteoblasts, remember osteoblasts build bone. And then lastly, calcitonin also affects the kidney, and it tells the kidney to excrete any excess calcium ions into your urine. So these are two great pictures, summary of how those three same areas are affected by these two hormones, and you will need to know this very well. Okay, so now we're going to talk about fractures and even about different types of bone fractures. So first of all, this fracture in this picture looks pretty terrible. Give you seconds. What bone is this? I think you know. This is the femur. You can see your greater trochanter and your lesser trochanter. There's the head. Here's your neck. So somebody had a really awful break in their thigh. That looks terrible. It's cool though. You can even see the medullary cavity here. So we know this is this looks like an adult. I can see the epiphyseal plate right here. So not plate, I'm sorry, the line, which means that yes, this person has stopped growing. So they're definitely an adult. Okay, so fractures, these are where you have cracks or actual breaks in the bone, and there's different levels of fractures and different types of fractures, and we'll talk about those. They are caused by some sort of physical stress, and certain types of stress cause certain types of fractures. So first we're going to quickly talk about how fractures are repaired. The first step, if any of you have ever broken a bone before, is you know there's a lot of pain and a lot of swelling and bruising. Well, that bruising, that's bleeding. We know that our bones have a very good blood supply, very, very good blood supply. So if they're damaged, yeah, it's going to bleed. But one good side benefit of that is that it heals quicker because you have a good blood supply. But first you have to deal with the bleeding and the bruising. And so at the place where the fracture actually occurs, you get bleeding and it forms a clot called a fracture hematoma. Hematoma is a big blood clot. And this helps start forming, as it says, a fibrous network, which is kind of where the healing is going to begin and form what we call a callus. In the area of the actual damage, the bone cells do die. But never fear, we have our osteoprogenitor cells. Remember, those are our stem cells, so they can produce more bone cells. Okay, then number 2, second step, cells in the endosteum and periosteum are going to have an effect in helping to heal a fracture. So in both of these areas, endosteum and periosteum, we have osteoprogenitor cells, osteoclasts, and osteoblasts. And so they are able to divide those osteoprogenitor cells, make osteoblasts, and they are able to go to the fracture zone and start repairing and depositing bone, and osteoclasts are there as well to help remodel the bone in this process. So as I mentioned above, callus is formed using that fibrous network, using early deposition of bone, and it helps stabilize the bone. It is by no means healed at this point. You have an external callus and an internal callus. Okay, external callus is made of cartilage and bone, and it surrounds the whole break. And then your internal callus is within the bone itself in the medullary cavity. Okay, the third step of fracture repair involves our osteoblasts. Remember, osteoblasts build bone. Okay, and so what these guys do is we have this cartilage callus that's formed where the fracture occurred. Osteoblasts are replacing that cartilage. Replacing the central cartilage and of that callus with bone. And notice it's replacing that central portion with spongy bone. Okay, so first spongy bone is laid down. Well, first you have a cartilage in the callus. Then you have osteoblasts that put down spongy bone. And then over a period of time, step 4, osteoblasts and osteocytes remodel that fracture, which can take up to a year, reduces the bony callus. And then, so if, say, if it was that femur, yes, the spongy bone on the diaphysis, the shaft of the bone, would eventually be replaced with compact bone, and then that medullary cavity would eventually be restored. But it can take up to a year to have this whole process occur. Excuse me. So this picture here just kind of takes you through those 4 steps. It's a nice visual. So this is another great one for you to just read through, review kind of the major things that are happening in the 4 major steps. Okay. Now we're going to go over different types of fractures. So first we're going to talk about pot fracture. And by the way, you do need to know the different types of fractures. So if in a question I describe a certain type of fracture, you should know the name of it. Or if I give the name, you should be able to know what kind of fracture that is. And you'll see as we kind of go through these examples. So first of all, a pot fracture is happening at the ankle. So these are our tarsal bones right here. Actually, this is the talus. This is our lateral malleolus of the fibula. Over here is our tibia. You can see the break here of the tibia and kind of the break here of the fibula. So a pot fracture is an ankle fracture and affects both bones, as you can see in that picture. Next is a comminuted, I think I said that, comminuted fracture. And okay, so this is the knee. So this is our intercondylar eminence. Okay, this is the tibia. Up here, this is the distal portion of the femur. So this break occurred right above the joint, which is really an awful place. And so this is kind of a shatter. And so it affects, you have a lot of bone fragments. And so this is going to require a lot of work to fix and heal. A transverse fracture. And in this picture, by the way, this is the radius right here, and this is the ulna. And so here's our transverse fracture, and it breaks it across the axis. So transverse, remember our plane, so a transverse plane is kind of like our horizontal plane. It's an easy way to kind of explain that. Or often when I give you guys examples, I say, okay, this plane could cut your neck off. I mean, not your neck off. I'm sorry, this plane could cut your head off because it's going at a horizontal plane. So a transverse fracture is going to be going in that same plane. Okay, next, spiral fracture. So if you look closely at this picture here, this is the tibia. Here's the fibula. So this is the ankle. This is our lateral malleolus, our medial malleolus. This is the talus. So this is the tibia here, and a spiral fracture is it's not cool because it is produced by twisting of the bone, and so the actual fracture, you have this twisting pattern. In fact, I have one of my best friends, we worked at summer camp for years, you guys know that, that she had an accident where she fell off the horse, but her foot got caught in the stirrup for a bit, and it twisted her, and she actually got spiral fractures of both the tibia and the fibula, which is actually very rare to have both of them have a spiral fracture at the same time, which shows just how much torque and twisting occurs. And so spiral fractures, I don't like those because you think about the twisting of the bone. Then talking about displaced fractures, this is where you have a fracture and it's not in its normal alignment. It is out of alignment, as you can see in this picture. You would have to have surgery to align these bones back into position because it would not be able to do it on its own. Okay, a Colles fracture. And what are we looking at here? This is somebody's arm. This is the ulna. You can see the little styloid process of the ulna. Over here, this is the distal portion of the radius. And so the styloid process of the radius would be here. I see an epiphyseal plate. You see that clear line right here? This means that's happening in someone who's still growing. I see another epiphyseal plate right there. So this is in a growing child or young adult. So this fracture occurred down at the distal end of the radius. And so notice it's very typical when someone reaches out to cushion a fall. And so this is a very common break. So when someone braces themselves to fall, like a lot of snowboarders, for example, wrist breaks or breaks in this area are very common. Okay, next is a green stick fracture. This happens in children. And instead of the bone actually breaking, it bends. So it's called a green stick fracture because if you've ever tried to break a twig that is still alive, it doesn't just snap, it bends. And maybe part of it snaps, but the whole thing doesn't snap. And so you kind of have that sort of thing happening with the bone because in young kids, the bone is more flexible. You have a lot of collagen. It's more flexible than an adult bone, which would snap easier than a children's bone. And so we get that same type of effect we'd get with a green branch if you tried to snap it. So only one side of the shaft would be broken, or have a part broken off or a part attached and kind of like a sliver off, and the other part's kind of bent a bit. And so yes, this happens mostly in children, as I mentioned. And then a really unfortunate one is an epiphyseal fracture. And so first of all, let's note, okay, this is the distal portion of the femur. This is the proximal portion of the tibia. There's your intercondylar eminence there. Right here is the epiphyseal plate for the tibia. Right here is the epiphyseal plate for the distal portion of the femur. And this portion of the break occurred right across that epiphyseal or growth plate. And that can be a problem if it is not healed properly. Okay, so I'll let you read what it says there, but doctors, modern medicine is really great. We're able to help. So when these happen, these are in children who are still growing. If the epiphyseal plate is damaged, it can lead to a body part, like an arm or leg, depending. So like if we're looking here at the femur, perhaps not being able to grow anymore in length. And so they'd end up with one femur being longer than the other. This was very common before more modern medicine with children. If they broke it along an epiphyseal plate, they would have problems for the rest of their life. They would have a short arm or short leg and have that problem. But we are able to, there's many ways we can help children and young adults who have epiphyseal fractures not have those long-lasting effects, but they are serious. Compression fractures. Really good example here is of the vertebra. So we notice here's a nice healthy body of the vertebra. Here's another nice healthy one. This vertebra has been compressed. Okay, so this is the body of the vertebra. And so compression happened on both ends, and this can be from a lot of stress or pressure. So it mentions, so if you land on your seat in a fall. So I met a man who was over in Iraq, and he was in an accident on Humvees, and they hit I can't remember, it wasn't a landmine, or maybe it was. Anyways, their Humvee went over it, and so it blew them up into the air. And so he said his head hit the roof, So you had compression going upwards, and then the car slammed back down. And so then as he fell back down on his bottom, then he had compression downwards as well. So you had compression from both sides. So this young man was telling me about that. And so when I see this picture, I always think of that veteran where he had compression basically along the entire length of his spine from both directions. Okay, good definition, osteopenia. This is something that occurs with age. Bones get thinner. Usually we say that happens with women. It does happen with men too. And they get weaker as well. And so this occurs around 30 to 40 years of age and then continues to progress with there. So notice it is unfair, ladies, but women lose 8% of bone loss per decade, while men only lose 3%. Can you remember why women are more at risk to losing bone? If someone said estrogen or menopause, you're correct. So just remember that at menopause, estrogen is no longer being produced. Estrogen is one of those hormones that helps stimulate osteoblast activity. If that hormone is no longer being produced, which is what happens in menopause, osteoblast activity is not as well regulated, which means you're not depositing as much calcium on the bone, and that can lead to more bone loss, brittle bones, and osteoporosis. Okay, so more on osteopenia. The places that are most affected, the epiphysis, so the ends of long bones, vertebra, and jaw, so the mandible. So with the vertebra, compression ends up happening over time. That's why typically older people seem to shrink with age. It's because they have this slow compression of the body of the vertebra over time because of bone loss. So yes, reduction in height, fragile limbs. It's more common for older people to break bones. Really commonly, the hip is a very, very common one. And then tooth loss as well. Osteoporosis is different. This is more severe, more serious. And this usually affects people over the age of 45. And notice again, the percentage of women is higher than men. We already know why. Remember, estrogen, menopause. There also is lifestyle, whether people are exercising and getting the proper nutrition. We know there are other factors as well. So this is a picture showing, this is osteopenia. This first one here is normal spongy bones. So what we're seeing is trabeculae, those little branches. What's neat is if you look really close in this picture, you see these little dots. Those are the lacunae where our mature osteocytes are living. So we still have lacunae and osteocytes in spongy bone, but we do not have osteons. Remember that. You only have osteons in compact bone. And then we look over here at number B and go, oh my goodness, that's terrible. This shows the bone loss. This shows the pitted trabeculae of the spongy bone, and it is less dense. It's very fragile, easy to break. Pretty big deal. So the effect of aging on bone. Okay, well, we have talked about estrogen, so hormones and bone loss, estrogen and androgens. So remember, androgens is a general term for sex hormones. Specifically, the big two, in addition to estrogen, you have progesterone and testosterone. So all three of those help maintain bone mass. And as we talked about before, at menopause, our main sex hormones are no longer being produced, and so that no longer helps maintain or prevent bone loss. And so women, their bone loss is accelerated because of that. Okay, cancer can also affect bone loss as well. So cancerous tissue releases what we'd call osteoclast activating factor. We know our osteoclasts, they break down bone. All right, And so it's stimulating the osteoclast to work harder, and that can lead to severe osteoporosis. And we are at the end of the chapter. So moving on to the next chapter, I believe it's chapter 9, and articulations.